Switch on the microphone. All right, give me 1 sec here. Wow, that's not what I want. Does it show up like that? All right, stop the video. Boom. And then, yeah, sounds like I have a lot of some big shoes to fill. Yeah, so I spoke, I can't remember if it was last year or like 2 years ago, on like GPUs and pipelines and things like that. As Steve said, I do tend to focus more on like the application side of things. Let me get the slides up here. And today's topic is about modern machine learning pipelines. So who here uses Python on a daily basis? Okay, everyone. Yeah, who here uses C? Yeah, all right. Yeah, any Go people? Any wacky Go people? Yeah, no one from Google. Okay, yeah. All right. So most of the talk will be about Python. I've got all the Python notebooks that are out there. And I'll send a link as part of this presentation as well. Also, there's been quite a lot of activity over the last 12 months with these open source technologies for machine learning. Specifically, there's new projects by Tensorflow, which comes out of Google. There's been some sort of new developments in that area. There's this project called Keras that got merged in. The Google folks actually hired the guy who created Keras, and it's now part of the TensorFlow API. There's also been quite a bit of movement here in the Bay Area, people leaving Uber and starting, various companies, people leaving Pinterest. What's happening is these larger companies have built out these just crazy complex pipelines, machine learning pipelines, to do feature engineering, to do feature combining, feature joining, and then all of the reproducibility of machine learning pipelines, all this kind of stuff. And they've either gotten themselves into so much technical debt. This is what one person told me, that they wanted to go off and start a company and just start from scratch, but take all those ideas. So I'm gonna mention a few open source projects and a few sort of budding companies that are starting. I should probably explain who I am first. So I founded this company, Pipeline AI, about 3 years ago. Really, the focus is more on the real-time machine learning side. So this is sort of rapidly iterating your machine learning pipelines, also online experiment tracking. So versus sort of offline experiment tracking. And by, yes, experiment, I mean training models and pushing them into production. So before I was at Databricks, which some of you might know came out of Berkeley, the Spark, it's the folks behind Apache Spark. So I was a field engineer, also doing quite a bit of ML there. I have this class with the O'Reilly folks. It's called High Performance TensorFlow in Production, where we talk about getting these models into production and then, so what happens after that. Also, I run a pretty big meetup. We have about 12,000 members, the Advanced Spark TensorFlow meetup. It's based up in San Francisco, but we're always up and down the Bay Area, so check that out. And what actually brought me from Chicago out to the Bay Area about 10 years ago was Netflix, and I was part of the original streaming team and going global and making your guys' recommendations a little bit more relevant. So yes, I predate a lot of the original programming that Netflix does now. So yeah, so those guys have it super easy now because they know what people want and they just go create it. Whereas my job was to force you to like something, right? Yeah, out of the crappy catalog. So I want to start with a little kind of Bay Area fun here. We were recently doing some fundraising for the seed. We were up and down Sand Hill Road everywhere. And we are starting to approach 4,000 stars. And one VC, actually very, very prominent VC right down the street, said, okay, 4,000 stars, once you get there, we can give you $6 million in seed funding. And I was like, where'd you get that? And they're like, that's just the number. And so you can kind of back into it and say, $1,500 per like GitHub star. So please go out there, because I think with enough of you, we can get, maybe 3,800, something like that. Yeah, 37.5. And yeah, this was, like pretty surprising. Yeah, has anyone actually gone and tried to do the fundraising? This is like a huge eye opener. I mean, yes, I use much different language now than I did, a couple years ago before this, where I was more technical. Now I'm all, talking about pillars and all kinds of, goofy stuff. Just to please these guys. But all right. So also, I've got some surveys that I'm going to throw in here every now and then. This was a survey we did about 3 weeks ago, and it's like, what are the popular ML frameworks that people are using today? And so this was about 500 people that we got responses from. These won't add up to 100 because it was multiple choice, but some of these should look familiar. And we'll actually talk about CoopFlow today. We'll talk about Tensorflow Extended, Airflow, MLflow. If you notice, there's a lot of flows and a lot of things. So I'll explain some of those names here in a bit. There's a project out of Facebook called PyTorch. There used to be Torch, and it was written in Lua and forced data scientists to learn Lua, and that didn't really go much beyond the Menlo Park campus. But now there's PyTorch, and it's kind of getting a little spike, but like my personal feeling is there's so much momentum with TensorFlow and Keras and things like this, and so TensorFlow has been around now for about 4 years, right? It came out in 2015, I believe. So TensorFlow is on 2.0, PyTorch is on 1.0. It gives you kind of a relative idea of where these projects are. I don't know a single company outside of Amazon that uses MXNet, but if you guys do know, let me know. But yeah, MXNet's kind of, actually that didn't even make the list. And then also, let's see, GPUs, TPUs. We won't talk too much about those. If you look up that like HPC console thing, you could probably find an old talk on GPUs, TPUs. All right, and so what is an ML pipeline? There's sort of roughly 6 different systems. Yes, I've had people actually argue that you could split system 2 into 2 and 3, and so each component could be its own system. These things can get as complex as you want. The sort of high level is there's this data transformation. There's sort of ETL, right? But this is not just strictly ETL, right? Like not just the extract, transform, load from the 70s and 80s, but this is actually doing like feature engineering. So this is a very, very heavy topic. It's a topic not a lot of people spend that much. Well, sorry, it's something that not a lot of people talk about, but there's that's really the majority of where time is spent is in that system 1. We'll talk about this library called TFX here in a bit that comes out of TensorFlow, which comes from Google, that actually helps you with the data validation step. And so this is a step that usually you would do in a Python notebook and have to kind of do it manually. And this project called TFX, which is a bunch of libraries that work with TensorFlow, sort of help you visualize your data and see where there's anomalies and help detect that. So, and at a very scalable way as well. So data splitting, that's where you're splitting data into sort of training data and then validation data, and then typically there's like one more holdout set, which is called test data. So we'll get more into those here in a bit. And then, obviously system 3 is where we're building the model. That's usually kind of building it in a sort of one-off ad hoc manner. And just kind of looking at the model, maybe running some slices of data through it to make sure that there's no bias or that there's minimal bias. And then what you do is go to system 4 there, which is actually distributed training. So this is spreading it across all the nodes in your cluster, or as many resources that you can get. And so the reason those are like system 3 and system 4 are in separate systems is because they're very different like infrastructures. So system 3 could be just a laptop or one single dev server out there, whereas system 4 is the real deal. That's the production system that is running at scale and then running all the time. And then system 5 is also sort of an area people don't really talk about too much. I've heard some people call like System 5 sort of the like easy part of machine learning. This is where you actually productionize your model. And so one of the reasons I created Pipeline was to sort of highlight that System 5. There's actually quite a bit of stuff that we did at Netflix when we like productionized like these models. So things like online A/B testing and multi-arm bandit testing, these are very important when you're actually putting these things like behind microservices. And then System 6 is kind of a cross-cutting. This is where I just dump everything that no one ever wants to talk about, right? The like monitoring, logging, and all that. But and so one thing we've seen over the last 2 years actually is these cloud providers. And yeah, I have a slide about Google Cloud and like Amazon SageMaker is a product from like Amazon that make all this simple. So all the logging is done for you. It's all integrated with the Amazon logging. They can do the serving, that System 5 pretty easily. And now they're starting to back up into the pipeline, into that like model training and then training at scale. Yeah, has anyone seen this or read this paper? This is one of the most famous papers on this topic, which the key here is there's this hidden technical debt, right, that's in machine learning. This is out of a NIPS paper from Google, I believe 2015, so, or 14, sort of around the time that like TensorFlow was being used internally by Google and then like eventually open sourced. So the like big realization here, and this is relatively to scale, is that like the actual machine learning code is just this little tiny box, and all the rest of it is what you need to really productionize your system. So here's that System 5 infrastructure, serving, monitoring was over in System 6. Feature extraction, that was that System 1 or 2 up there on top. And then yes, all the resource management, process management tools, monitoring. Oh yeah, by the way, speaking of VCs, they all know this paper. So if you're going for any funding somewhere in the machine learning space to tackle one of these problems, they will all reference that hidden technical debt. It's called like the high interest of hidden technical debt or something. There's like a fuller name for it. Okay, so at a high level, what's the problem that these like ML frameworks and pipelines are trying to solve? Well, there's complexity. Yes, I just showed that. There's also quite a bit of fragmentation and not a lot of consistency between these tools. And as you start to bring on more and more machine learning experts, they have their own tools. They use their own specific libraries. Yes, right, like everyone pretty much uses scikit-learn. Starting to see more and more people use TensorFlow, kind of unify around that. Some people are very, very strong about PyTorch, which can cause problems when the whole rest of the company is dealing with TensorFlow. Also, the big point I'm trying to make here with these pipelines is that traditionally these pipelines have been sort of one shot or sort of linear, and it's a train and then forget. And so one thing I want to like highlight over and over is that we can iterate and learn from the model that's in production, right? These like models can actually decay over time. Think of a fraud model that's been pushed out, and then within like 2 hours someone has actually defrauded this model. So training and forgetting and not having that monitoring set up, right, to detect decay and like detect drift, and these are other terms that are used for this like kind of problem. And so the ability to actually iterate and continue to improve these models is very, very important. Okay, so some notes on the infrastructure, and I threw a singularity slide in here just to make it seem like I understand all the HPC stuff, but that's not really my specialty. Yeah, sorry guys. One thing that is true across all of these modern ML pipeline infrastructures is Docker. So if the sort of unfortunate thing, and I think you're like mostly systems people here, right, like you get Docker. You can see a Docker file and see where we're pulling in the pip requirements and Python libraries. And one sort of unfortunate thing about the current state of these pipelines is that while this stuff is fun for us systems people, it's not really fun for the data scientists, right? They shouldn't have to think about a base Docker image and how these things are being loaded, and maybe a Conda environment is getting messed up somehow in this like Docker build, which was top of mind because it just happened this morning. So Docker's fun for us DevOps, but it's a bit clunky. We will always have one Docker image per batch job. So batch job meaning a training job, model training job. We will always have one Docker image for a model server. That's when we're actually pushing the model into production, and we've trained the model with the batch training and then slurped it into this Docker image. And yeah, I came up with that little diagram up there with the Docker thing and then eating all those models. The other common thing that we'll see is Kubernetes. And so, yeah, I realize, right, like you guys all kind of have your own schedulers and things going on. Like Kubernetes is the king right now. If you're familiar with like Mesos and some of these other sort of data center technologies, and what's really at a high level called like container orchestration. Yeah, so Kubernetes has become the clear winner. And if you notice, Kubernetes and CoopFlow, that term CoopFlow is because of Kubernetes, and then CoopFlow, the flow is from Tensorflow. And these are both technologies out of Google. And yeah, like we'll talk about CoopFlow here in a bit. But really, Kubernetes is sort of like the new Linux. I was just like joking around with a friend the other day. She kept like bringing up Kubernetes all the time, and I'm like, right, like, why do you bring up Kubernetes? This is like bringing up Linux. You don't really talk about Linux anymore, right? Like you just kind of assume it's there. Or like Kafka, for example. Like you don't really talk about Kafka. You just talk about the streaming use case. You know that people are using Kafka. So, but it's still fun and hip and has a cool logo. I think a Kubernetes, it's some kind of sailing reference or something. I think it like manages the Docker containers. I don't know. There's some kind of nautical theme going on with all this stuff. But the logo is pretty cool. It's got the little steering wheel or whatever. And so Kubernetes, fortunately, has started to become the new standard now for these batch jobs and for cron jobs. So things that we would typically do at the command line. You can now basically create like a Kubernetes manifest file that calls that same cron job, but it's being scheduled by Kubernetes and has all this nice monitoring and can actually restart if it fails. And yeah, so Kubernetes is super active. I think they're up to a 1.16 or 1.15 release. And it's taken about 3 or 4 years for like Kubernetes to actually become popular. Yes, I remember one of my friends left Netflix and went to go work on this project called Kubernetes with Google, and I was like, what the heck is that? Just go work on Mesos, And then, yeah, a couple years later, now it's the new standard. And then quick survey from folks the first week of July. We see most of the Kubernetes clusters, and yes, this is very, very interesting. Like this is one of those business concepts that I've been picking up as I've been like running this company, which is the creators of Kubernetes and TensorFlow is Google, but that value that's been like captured is actually from Amazon. And so this is kind of expected. I mean, if you looked at the other dimension, it would be Amazon Web Services has 65% of the market, and then Google Cloud has like 4 or something %. So, kind of makes sense that, yes, Amazon can actually capture that value. But yeah, Google's trying a few different things to get Google Cloud to become popular. They, created these TPUs. You can only use TPUs, which are much faster than GPUs. But like you can only use them if you use Google Cloud. Those TPUs can only read from Google Cloud storage, so you have to move all your data into Google storage. There's kind of that thread that you start pulling. But yeah, so Amazon is up to speed on the latest GPUs and is pretty much good enough for everyone. And yeah, these cloud providers actually have their own Kubernetes services now. So it's managed Kubernetes so that you're not actually, right, like, like restarting these, Kubernetes processes and like doing your own upgrades. You could actually have these cloud services do the upgrades. Okay, I think this is probably the heaviest slide here. Characteristics of a modern ML pipeline. So, and then next to it is a survey from that same time, first week of July. There's some stuff here that's online, just kind of skip that for today really. Although, yeah, it's pretty high up there. People, so this is from a workshop that we do each month, and we cover all these, and what we were trying to do is figure out at the beginning of the class, what are people interested in? They want reproducible experiments. I think the highest is the deploy models into production. That's also an area that we specialize in, so it's a little bit skewed. And then, yeah, the A/B testing and multi-arm bandit testing of these models. So the ability to put two versions of the models out and track what version was shown to which user, and then figure out which ones are the most popular. Some of the ones I thought would be higher up, but aren't, are the training data, the ingest. Feature engineering I thought would be a little bit higher, although it's 30, well, yeah, this isn't, yeah, like these don't add up to 100 here, but. And then sort of ad hoc data analysis was actually like a bit lower than I thought. So people are still in this batch prediction mode. So I should like be very clear that when I talk about deploying models into production, I'm talking about right, like this sort of high velocity REST endpoints, right? So the ability to log into Netflix and start right, like making calls to this microservice. And that's in contrast to batch predictions, which is here's all my users, here's the catalog of all the movies that I have, and just do an offline calculation to figure out which ones are the top like movies to show to that user when he or she logs in. Okay, so characteristics of a modern ML pipeline. We'll dive into these in the subsequent slides. So the big one is this concept of tracking experiments. So how do we make a small tweak to our model and then like rerun the training and then see the results and the, you know, see the like accuracy, see like various metrics that we're trying to track. There's also hyperparameter optimization, and I want to put this in top because this is what's driving quite a bit of innovation and startup movement in the Bay Area. There's a lot of companies. There's also the like cloud providers that are starting to do hyperparameter optimization. If you're not familiar with a hyperparameter, so hyperparameters are how the model learns. So these are parameters that you can pass in. So the classic like example would be decision trees. How deep of a tree do I want to try to build off my data? Is it 10 like levels deep? Is it 50 levels deep? At some point, you'll start to overfit, and that model can't generalize to other data sets. And so these are what's called hyperparameters. A parameter is what you're actually learning. So you have like a set of points, you're trying to fit a line or fit a curve, right? Those are the parameters that you're learning, but how those are learned are with hyperparameters. And so hyperparameters aren't usually top of mind for people that are just doing ad hoc, sort of like notebook-based like machine learning, because they require tons of compute. And these cloud providers love it because if you are super like curious, I guess you would say, where I could just change this value a tiny bit and then let me see, yes, I'll let it train for a day and then see, or do them all in parallel. So I'll do 0.1 for or I'll do 10, 20, 30, 40, 50 levels deep. And then I was just at a talk by the OpenAI guys. They said that they go crazy with this stuff. They have like so many different hyperparameters and like different combinations, right? Because it's a like combinatorial type problem. So if you have multiple if you have multiple hyperparameters, there's going to be all the different combinations. And there's something called grid search where you try all of them, right? Which the cloud providers love because it's, you know, tons of compute. Or you sort of randomly select, which is one I'll show here in a bit. And then there's something called Bayesian optimization where it's sort of learning and then adapting which hyperparameter combinations it's going to try next. So yeah, lots of startups working on this. And then also distributed parallel execution. So this is kind of fundamental to hyperparameter optimization. You typically want the answer right away. You don't want to wait sort of linearly to try one combination, try another one. That's just going to take months and years to do. So do these in parallel. Yeah, so you guys are all familiar with parallel like execution, so I'm not going to spend too much time there. Oh, and so hyperparameter tuning or like optimization, yeah, so that's one other term that these VCs know, by the way. So they know how does it go? Like they know one of them, but not the other. If you ask them about hyperparameter tuning, they're like, I don't know what that is. And then you say hyperparameter optimization, they're like, oh yeah, okay, HPO, because that's what they heard in one of their partner meetings or something. With like hyperparameter optimization, this is like naturally parallelizable. There's the other kind of like parallelization of one single like training run that you're doing, and then having multiple servers talking to each other. So yeah, that's a little bit trickier. Tensorflow is getting a little bit better with this across nodes. Up till now, for the last 3 or 4 years, it's been very, very manual and kind of cryptic, right? Like yes, internally Google has a better way to do it, but yeah, so outside of Google, it's right, like kind of hokey and sort of ad hoc. The other concept here is like metadata. So like the ability to store, so these like ML pipelines have various components. There's the feature engineering, there's the raw data coming in, then there's some kind of engineering happening, and then there's outputs. So there's like quite a lot going on in the CoopFlow world, also TFX world, where these metadata stores are becoming first-class citizens. And then I'll talk about FeatureStore here in a sec. That's another very interesting one. But back to the metadata, and then experiment reproducibility. So like oftentimes there's a need to kind of go back in time and see, how did this model get like this? What was the data that was used to train? This is a very like complex problem. There's only a couple startups that really focus on this. The cloud providers have been taking their sweet time here. Not quite sure why, but it's a pretty complex problem. It's the sort of simple way to do it, which speaking with one of my like Google Brain buddies who worked on Street View, trying to like block out the little like license plates and people's faces. Yes, I asked him, because this was 2014 or 15, how did you do data versioning? And he said, I just created a subdirectory for that date and for that experiment. And it was just a copy of all the images that they were training on. So yeah, it was just some shared file system somewhere. And there wasn't much beyond that. So like data versioning is kind of one of those problems where you can get around it. Maybe it's a little bit more expensive, but it's not really worth engineering, doing all this engineering around it. Yeah, but hopefully that's going to get like built in. So think of it sort of like GitHub for data, right? The other two here, so detecting this model like bias. So this is, you've trained the model, you have some data that you've held out that the model hasn't seen. You really hopefully have a nice equal balance of all the training or of all classes that you're trying to test. And now you can kind of feed it into the model. And this is all through Jupyter notebooks. And see, right, like how on this particular slice of data is my model completely biased or skewed towards one particular gender, one particular race, something like that. So these are like provided to us in the form of libraries that like Google has given us as part of TFX, and yeah, I'll show those here in a bit. But they are TensorFlow specific. That's the one caveat. This concept of decay, I like had already mentioned about model decay, and then drift. So there's this concept called concept drift, and what's happening here is the model has been trained with a particular distribution of data that it saw during training. And now the model is getting some new data that it hasn't seen before because it's out in the wild that is different than that distribution that it was trained on. So the predictions are starting to really come across a little crusty. So this is all like part of this concept of sort of iterative machine learning and not fire and forget or train and then forget. This last sort of element, FeatureStore, is actually one of the kind of oldest concepts, but the most recently, there's a lot of excitement going on. So yes, I have some friends that actually just left Uber to start a company specifically for FeatureStore, and so their whole thing is or the problem is, so Uber was so big that there were so many different teams doing feature engineering, and they would find like significant features. So they would combine the trip duration with the tip, with the this, with the that, and then found it useful for the next models that they were training. And like without having a big Slack channel to post this to, or having like all hand meetings every other day to figure out which features are the most relevant, they started to build what's called a FeatureStore. And so think of it like a data warehouse for machine learning, right? As crummy as that sounds, but think of like the ability to go in and like discover new features that have been significant for other teams. And it's not just what the features are, but it's actually the like materialized set of features that have been combined or found to be useful. So the reason why the Bay Area is getting really excited about this and Sand Hill Road's getting super excited is there's tons of data here. VCs love data because of the gravitational pull that these companies have to customers. And yeah, it's pretty useful. The downside is it's in like my opinion, this is really only useful for kind of the top tier companies that have so many people that they can't communicate these features. And it's one of those where in that case they've usually built this already or have some form of it. But yeah, so we'll see how that plays out. Okay, I think I probably mentioned this, so let me there's typically, for the experiment tracking, there's a single cluster that is the tracking cluster or tracking server. I'll show you like a picture here. So this is actually MLflow. And I haven't really talked too much about MLflow. This actually comes out of Databricks. So the people that created Spark from Berkeley, they got kind of frustrated with the current landscape. And so I'm kind of starting at my personal favorite right now, and I'm a little bit biased because I used to work there. But it's super clean. The Python libraries are super clean. There's R support, which is like surprisingly still very big. And there's Java support, Spark support. And so you can kind of put all of these different models into one view. So like you could train a model with Spark, you could train the model in Keras, and then have them all show up. And what we see here is the date of the run, some other metadata. These are the hyperparameters. So these are specific to the type of model that's being trained. So this would be like the depth of your decision tree if you're using decision tree. And then these are the metrics that you've looked at. So you've held data out, and you pretend like that model, so that model hasn't seen it. So you pretend that you don't know the answer, and then run it through, and then compare it to the actual answer. And that's what gives you the root mean squared error, where you take the prediction from the model, and then the actual value, and then compare it. And so what you want typically are low values, because that means that there's low error, or there's very little difference between what the model predicted and what the actual value is from this validation data set that you've held out. And there's cool ways you can compare and show some slick visualizations. See if we have time for that here in a bit. Okay, and I talked about hyperparameters, I think, pretty good. One thing to point out again is hyperparameters are different than the actual model parameters. Okay. So this is what the model's learning. And one thing to highlight here too is that the actual, so this is a very complex neural network called the Inception V3 model, used for image classification on 1,000 image classes, penguins and pianos and things like that. This architecture didn't just show up overnight, right? This is actually a hyperparameter. How I'm constructing this neural network is something that I'm going to test. And I'm going to train my model, I'm going to compare the actual, and I'm going to try to minimize that error that I showed before. So yeah, this just happens to be, for this data set, a pretty good model to do this. And there's been 3 or 4 iterations, I think, since this particular model. But yeah, these connections, so these are all layers, and they're all connecting to other downstream layers. So the bullet point there is that the actual neural network architecture is something, is considered a hyperparameter. Okay, this is called parallel coordinate plot. This is actually pretty cool. It's showing, so yes, let me back up a sec. This is hyperparameter tuning. This is the random search. So we have 3 different parameters that we're trying to tune. We've got, I think it's can't really see it very well. It's the number of layers is one hyperparameter. There's another one, can't remember what it is, but these are all specific to this algorithm. And also that third is the actual optimizer that's being used. So, or different gradient descent optimizers, for example, or something called atom optimizer. And so we could actually change which optimizer per hyperparameter run. Okay, and then this is parallel coordinate plot, which is super useful to kind of trace through and see which plot actually. Oh yeah, so LR is the learning rate, which is a parameter, a hyperparameter that this particular model uses. What we're trying to do is to maximize the accuracy, specifically validation accuracy, and we can then go look and see which hyperparameters actually fed into that. One thing that's probably pretty relevant to the HPC world is as of TensorFlow 1.13 or 1.10 or something like that, which was about a year ago, there's something called hierarchical copy all reduce. So it's a first-class distributed training mechanism or strategy that's offered by TensorFlow. And this has been carried into the TensorFlow 2.0 stuff, which is very important. Because between TensorFlow 1 and 2, they've actually deprecated and made a bunch of changes. And then, yeah, this is what you get when you run multiple jobs. You have different workers that are each producing, and let's see. This is an example of that detect the model bias and decay, where we have different slices. They're kind of hard to see up there because they've been cut off, but you can see them down there, and see actually which slices of data, and then sort it by accuracy. And so this is after the model's been trained. Let's feed in data for one particular start time and one particular end time, and see what you want is even distribution across this, right? Okay, we haven't talked about TFX yet, but this is what an individual component within the TFX pipeline looks like. So I'll probably go past this quickly and maybe circle back to it, but yeah, so each component takes in data through the driver, does some kind of processing, and then writes it out again. So FeatureStore, this actually comes from, I believe, Airbnb's project that they have sort of internally called Big Head. Here's the traditional big data platform. Here's kind of the ML platform. There's something in between, which is the FeatureStore or the feature platform. And so some of these types of things that you want to pull out of the store, like I said earlier, you could cross different features. Maybe age plus income is very significant. And then gender balanced samples, things that you would rather not do if someone else has already done this for you. There's a project that's kind of loosely associated with CoopFlow, which is this Feast project. It's not actually part of the CoopFlow GitHub, so not quite sure where it's falling in. It seems like an independent project still so far. All right, so let's talk about the tools. And so CoopFlow is Kubernetes plus TensorFlow. It's really relying on a ton of other projects, beneath the covers. It's trying to put a nice facade. There's this project that came out of MIT a few years ago called ModelDB, which is actually how CoopFlow is doing its experiment tracking. And now this is different than MLflow, which I had shown you guys a few slides ago. So yeah, CoopFlow has its own way to track these experiments. It has its own metadata store, kind of has its own thing going on. CoopFlow is the one that gets the most buzz. It's also wildly complicated and just massively difficult to debug. It's very much tied to Kubernetes. Every release, we have to go in and pluck out all the Google-specific dependencies, Google Cloud-specific dependencies. It's a little bit wonky from that perspective because most of the people working on this project are from Google. It's very natural for them to leave in a few places where they make assumptions that you have a Google account and things like that. Has anyone used Airflow? For people that have used Python. Okay. Yes, Airflow comes from sort of traditional data engineering. It's a nice visual tool that can show you steps that are happening and then steps that are like happening in parallel, which ones depend on other ones, things like that. Airflow has been kind of repurposed now for machine learning. There's something called MLflow. That's a from-scratch implementation. Yes, like I said, those Databricks guys got tired of figuring out what was going to be the best standard, and decided to just go off and kind of clean room create. And so, yes, like I said, there's Python, there's R support, Java support. TFX is less of a pipeline and more of a collection of like nice libraries that can do data visualization and like anomaly detection. That's how we do the slicing, showing those different trips. And then there's a project called Pachyderm, and this is a Bay Area startup. Just got 10 million, I think, from Benchmark. So these guys are trying to tackle that like data versioning problem. And so instead of writing to the file system like directly or to S3 directly, you actually write through the like Pachyderm file system, which sits on top. This personally makes me very nervous because I get scared about file systems to begin with because they're, if something goes wrong. But yeah, they claim to have solved these problems and can do like recovering and like prevent data loss and that kind of thing. Pachyderm has also started to make a play at the ML and sort of AI pipeline space. These are all, actually I should say, CoopFlow is very Docker based. Actually just CoopFlow. And then Pachyderm, like Pachyderm is also Docker based, meaning every component in the pipeline has to be its own Docker image. So it's a little bit thicker weight, but can then participate in Kubernetes and all the fun stuff happening there. Whereas those three in the middle, Airflow, MLflow, TFX, are all just Python libraries. So Google created, it's basically Kubernetes plus Tensorflow. I use the term cobbled together. I don't think they like that, but that's pretty much what it is. There were like many standards that were happening. They pulled them in. They have this nice GUI that's pretty fun to play with, and you could watch these Docker containers running. Yes, CoopFlow is very Docker based. It's a 0.6 release, and this has been in the works for about a year and a half. So if you kind of project that out, maybe it'll be another year and a half before we get to 1.0. It's been traditionally pretty clunky. They've attempted to create their own standard, sort of like yet to see how that's going to play out, but it's been getting better, which is all you can ask really from this massive project. This is Airflow, familiar interface to a lot of data scientists or to systems people like data engineers, and you'll see like a lot of the. So yes, each of these is just a Python snippet of code, and we're like pulling in data through the CSV generator, passing it into the statistics generator to kind of look at the sort of overall mean standard deviation of the data that we're looking at. Extracting a schema, this is always useful. If we have blank data or really data that we don't know much about, let's try to extract some knowledge about it, make sense of it. We then transform it, we can validate it in parallel, which is why you have two branches coming off schema gen. Then goes to the trainer, so that's the model trainer itself, which is really what we're trying to do. All this is just to get to the ability to train the model. And then in parallel, we can actually evaluate it. And then we can also do model validation, sort of ad hoc model validation. And then ultimately push it out into production. That's what the pusher does, which can package it up as a first-class microservice and send it out. Okay, TFX. So I mentioned this a bunch of times. This is Google finally saying, okay, we've actually been holding back on you guys. We gave you TensorFlow. We went out and bought the person that created Keras and merged that in. So we're focused on kind of high-level APIs for machine learning. But really, all this time, we've had a much larger system called TFX, TensorFlow Extended. And so this is the whole, shebang here, right? So there's loading features, analyzing those features, transforming all the steps I was mentioning on the Airflow slide a bit ago. Training, evaluating, then ultimately deploying. One thing about TensorFlow that's kind of interesting is they have something called TensorFlow Serving, which is a C-based server that can read the output of TensorFlow's training or Keras's training model and can serve it up in C speeds. And it has a gRPC interface, a REST interface. There's also TensorFlow Lite, which is meant for mobile or for smaller devices, where it can quantize down the model that's been trained, simplify the model to make the matrix math faster, right? It's a lot easier to, it's a lot faster to multiply two 16-bit integers or floats than it is to do 32-bit floats, especially huge matrices of these. You can also deploy into the browser, so TensorFlow.js. TensorFlow.js can actually train models as well too, not just serve up predictions in the browser, but you could have multiple browsers that are participating in model training. But for this diagram, we're just pushing it out. And there's something called TensorFlow Hub, and PyTorch just released something called PyTorch Hub. And this term hub is, think of it, if you're familiar with Docker, you know Docker Hub, where you train, or you build a Docker image, push it out, and now the world can pull it down. So this is where you would train a model, push it to TensorFlow Hub, and then share those coordinates for this model or for this snippet of code, but primarily for models, and share it with the rest of the people in the world. And so if you're familiar at all with Maven and Ivy and some of those like Java package manager thing, I don't know if you're familiar with those, or pip, PyPy, where you give it coordinates and it can pull in those dependencies. Okay, commercial offerings. So yeah, Amazon has something called SageMaker. Yes, I don't work for any of these folks, so there's no. Google Cloud has something called the Google Cloud ML. It's similar to SageMaker, except I don't really think anyone uses it except Google. Uh-oh, there's someone from Google. Yeah.
I have a question regarding the previous slide.
Yeah.
What's the difference, like, if you were to search a model, what's the difference between using the hub versus TensorFlow Serving?
Yeah, you would, the quickest answer would be when you start up TensorFlow Serving, you would point it to a model that's stored in TensorFlow Hub. It'll pull it down and serve it. This is for you actually, hosting your own service. Google Cloud ML, SageMaker, you can upload your model, and it has a whole fleet of TensorFlow serving servers. Yeah, so that's a good question. This is really the runtime for predictions, and this is just like a database of models. Yeah. I'll probably get in trouble from my Google Cloud friends here, but I don't really know too many people that use it. I know a whole ton of people that use SageMaker, but yeah, we'll see. Again, this is the fact that Amazon has its huge market share, and then Google has very low market share. Azure, I haven't logged in there in about 2 years, so I think it's my old Hotmail password and old girlfriend's name. I don't want to mix those or whatever, right? But the other thing to mention here, speaking of Kubernetes, is all of these now support Kubernetes engines, and so Google, it's GKE, Google Kubernetes Engine, I think. Yeah, Amazon, it's, what is it? EKS, the Elastic Kubernetes Service. And then, Azure has something called AKS, Azure Kubernetes Service. So there's really two ways to deploy. Well, there's three. You could do all this on your own, Kubernetes cluster, and spin up your own fleet of TensorFlow serving servers, or you could use the cloud Kubernetes engines. And so you're not really managing Kubernetes anymore, but you're still manually creating Docker images and uploading them into the cloud, or just use one of these services that, like you could actually point to an S3 bucket or a Google Cloud Storage bucket, and then give it, or like TensorFlow Hub, and yeah, these will serve it. All right, so summary, ML pipelines are hot, hot, hot. Lots of tools. It's an exciting place to be, right? Yeah, we all are here for the innovation and for the $4,000 one bedroom or studio apartments. Lots of companies working in this area. So like I said at the beginning, there's a lot of people leaving these places to go create their own projects, create their own startups. There's a lot of money flowing around. And one thing, the area that we focus on is this more online type of stuff, experiment tracking. And really, we're falling into that category where you could do it yourself, but you have to cobble together so many things. So similar to how I was describing the data versioning, where you can just create another subfolder and not have to build a bunch of engineering. So I think we're still maybe a couple years out from actually doing online experiment tracking and online optimizations. It's a pretty complex problem, really only needed by kind of the top tier people. Yes, if you're familiar with things like Optimizely, these are web-based products that you can A/B test, one like HTML page versus another, one product page versus another product page, and see which one. That's kind of the idea, right? But more for sort of like back-end type stuff. So my big suggestion here, and I'm sort of informally like voting for MLflow right now. Stay simple and use like just what you need. And the problem is there's so many people looking at things like CoopFlow and TFX because of the marketing blast that they're getting every day in their inbox or their LinkedIn feed. And from a top down, it seems okay, but once you actually get into the weeds, it's very clunky. Partially because it's Docker based, and every component has to be a Docker image. And there's little tricks that you can do. You can, from a Jupyter Notebook, create a Docker image, and there's some shims in place that CoopFlow offers, but just kind of stick with like what you need. Cool. And then we have Community Edition where like a lot of those screenshots came from, and thanks for listening.